Hello, everyone. Welcome back to the class. So today we have a representative from the Women in Computer Science group that wants to introduce their organization to you. So let me introduce Regina. Regina, can you please take over and tell the students about your organization?
Hello, I'm Regina from WIX, from the Women in Computer Science. WIX is an organization whose mission is to provide support to women in the fields of computing. We host many professional and social events working with tech companies and College of Engineering CAS. Anyone can join our club regardless of major and gender. You don't need to be a computer science major or you don't and or you don't need to be a female to join our club. We host general events and women-centric events. Some events we host are craft nights, resume review, interview preps, coding workshops, and more. We host computer science and information technology networking events to connect students with companies, employers to help land you a job or internship. We have worked with the CS department, the Career Center, Google, Facebook, and much more. Our events are open to everyone. We welcome everyone, regardless of gender and major, to join us in our effort to provide a safe and inclusive environment in the tech field. So we'll be at both virtual involvement fairs this Friday and next Friday. Our first GBM, General Body Meeting, will be September 11th at 4 p.m. And you can find more about us on our social media links. Any questions?
Can you send the social media links?
I can send them to the professor and he can put it up Blackboard.
Okay, I'll definitely do that. Do you have anything more to add?
No.
Okay, very good. So thank you. And, once again, many times, again, when you're a first year student here, it's difficult to, find your footing. You really don't know, if you belong here and so on. And, WIX is a great place to, find like-minded people and to get some support, to understand what it really means to be a computer science professional, and also to see not just the technical side of things, but also how people interact with each other and so on. So again, I mentioned to you, my daughter went through this our program, and she found WIX to be invaluable. So you should really take it up. And another thing that Regina mentioned, which you may or may not have fully internalized, and that is that it's open to men as well, right? So anybody is welcome, and you might find it a very welcoming place, and somewhat has a somewhat different feel to it than the ACM chapter, which is for computer science, and this is I believe sort of a more supportive environment. I would say that's what I am. My daughter would describe it that way. So I think it's really a great place to check out. So I encourage all of you to join the group and benefit from it.
So thank you for listening and good luck on your class. Thank you, Professor. Bye.
Thank you. Okay, so let's see. Are there any questions? Did anybody have trouble getting into the class today? I mean, if somebody had trouble, of course, they won't be here, but somebody else might have noticed. And then if anybody saw anything, let me know. Speak up, right? And again, interrupt me often, because that's the only way to make sure that I know where you are, and to make sure that the class is at the level that's appropriate for everyone. Okay, so let's give me 1 more minute. I have, I'm continuing to have some issues with the setup. So just give me a minute and then we'll start the class. Okay, so let's get started for, the last lecture we went over some proofs, and the goal was to give you a flavor for interesting theorems and proofs. So one of the nice things is, of course, it's interesting, but at the same time, those are not the type of proofs I can expect, anyone in the class, including myself, to come up with in most cases. So sure, if you have seen the proof once before, you can, create something similar in the future. So what we are going to do is we are going to change gears a little bit today, and we are going to learn, material that's something that you should all be able to understand fully and be able to, internalize and, be able to solve problems based on this kind of material, right? So we are, to the extent possible, I'm going to follow the textbook. So you have, additional reference material that you can look at. And so when possible, I'll indicate the relevant, book sections. Okay, so you can see that, um, I'm okay, so this is the problem. Okay, so you can see that, I'm highlighting textbook section here. So that's where you would go for more detailed material on this. Okay, so let's start by defining what a proposition is. Okay, so a proposition is a statement. The restriction is that the statement should either be true or false. Okay, so so that leaves rules out certain statements as propositions. So for instance, sky is beautiful. You can't say it's true or false because it's something that's relative to someone who is expressing an opinion on whether the sky is beautiful or not, right? So if I said, Brandon thinks sky is beautiful, then that could be a proposition because we could, check, find out from Brandon whether he thinks the sky is beautiful or not. Okay, but without that information, we cannot determine whether it is true or false, and therefore it's not a proposition. Okay. Similarly, tomorrow will be sunny. It's something that's referring to what can be known only tomorrow, right? So right now we cannot say if it's true or false. Okay. So on the other hand, these are some examples of propositions. 2 plus 3 equals 5, right? So I could have also written, right? So I could write 3 plus 4 equal to 5. That is also a proposition. It just happens to be an incorrect proposition or a proposition that is false. Okay. So again, propositions, since they can be true or false, we are not saying anything about the whether a proposition is correct. We are simply saying it either is true or false. Okay. So now let's look at another example. N squared plus n plus 41 is always prime. Now, do you think this is true or false? Anybody wants to answer?
False.
Why is it false?
Well, if n is 41, then the sum is divisible by 41.
Right. So obviously, if you set n equal to 41, then n squared is divisible by 41, n is divisible by 41, and of course 41 is divisible by 41. So if you set n equal to 41, then you get you'll get a value that is divisible by 41, and therefore it's not prime. Okay. Although what you are likely to find if you just substitute small values of n is that the statement is actually true for many small values of n. So unless either you should try a large number of values of n, or what you need to do is you need to be clever and look at identify the structure in here and then say, hey, it's the 41 is the magic number to substitute, and then I'll have an example that shows that this is false. And such an example that shows that a proposition is false or a theorem is false is called a counter example, right? Okay. So there are many interesting claims and conjectures and theorems that have been proved over time. So a claim is something, claim or conjecture is a proposition, but we don't have any proof or any explanation as to why it is true or false. Okay, a theorem is one where the truth of that proposition has been established, okay, has been proved. So, so this is a very old conjecture by Euler. Euler is from the 1700s, so it's been around for quite some time. And it wasn't known for about 200 years, whether this was true. And if you look at the example, you'll see why, right? So you can see that you have to substitute rather large values of A, B, C, and D. And, before, modern computers, trying to do this manually to find a value that doesn't work is obviously very, very, very time consuming, right? So you can see that these are the smallest values of A, B, C, and D, right? So that's the point. So you tried any smaller value, you would not be able to find a solution. Okay. So here is another, so something called the four-color theorem. Many of you may have heard about this, and what it says is that if you have a map, and typically when we say map, we often think of the world map or a map that shows countries. And one of the things we want to do when we have this map is we want to give colors to different countries in such a way that no two adjacent countries have the same color, right? So this way we can clearly see the boundary between the two countries. And it was shown, it has been conjectured for a very long time that 4 colors are sufficient to color any map. But proving this, turned out to be quite difficult. And in fact, what happened is that we needed software because the proof is rather laborious, requires a very large number of cases to be tried. And so it took a while for this to be proved, and so much so that there is a book, right? So you can see this book, which was published in 2003 about the saga of proving this theorem. There was sort of a proof in the mid 70s, and then people were not quite satisfied with it. In the 90s, an improved proof was produced, and then that came to be accepted, right? So that's another interesting case. And then you might have heard of Fermat's last theorem, which basically says this formula x to the power n, or equation x to the power n plus y to the power n equal to z to the power n, has no integer solution for n greater than 2, right? So n equal to 2 is the Pythagorean case that we have seen many times. But for n greater than 2, this equation does not have any solutions. And Fermat said, famously said that I would have proved it, but in my notebook, it doesn't fit in the margin of my notebook. So I'm just going to leave it for the reader to work it out because there's really no space. And then, it took, more than 300 years for the theorem to be proved. So, and once again, there is a book that talks about this. And there is the last example, Goldbach's conjecture, which remains a conjecture even today, right? So what we know is that because we have computers, so we can try this if it is true for a very large number of values, right? So we have tried up to 10 to the power 18 and shown that every number is a sum of 2 primes, but we don't know whether it is true for all n. Okay, so anyway, that's just an interesting list of propositions, conjectures and the theorems that people have looked at over time. So now let's get back to understanding propositions better and how propositions are combined into logical formulas, right? So at this point, we are switching over to chapter 3, and then we'll come back to chapter 1 after some time. Okay, so there are often 4 operators that that we use for combining propositions: the AND operation, or the negation operation, and the implies operation. Okay, I think all of you know what these operations are, so I'm not going to try to define them. But as we go through some examples, you will of course, remember it if you don't remember it already. In particular, if there is any confusion, that should be only about implies. The other 3, no one could possibly say that they don't remember. Okay. So what we want to do as an exercise is to take some English sentences and turn them into logic formulas. Okay. So in order to do that, we have to identify parts of an English statement that are like propositions, and then other parts that are like logical operators, right? So I already identified that. So an AND is a logical operation, and if then is another logical operation, right? So now we have to identify what the propositions are. So that's one proposition. We'll call that P, and then we have Greeks are human, which is proposition Q. Then we have Greeks are mortal, which is a proposition R, right? So now we can write, so and is going to be just the and connective. So we can say P and Q, right? And if then becomes the implies operation, right? So if we turn that into a logical formula, this is what we will write. Okay. Any questions so far? Okay. So I guess maybe in order to get a response, maybe I have to purposely write do something wrong.
I have a question.
Yeah.
So I kind of missed the previous slide. Like, do you have the slides up on like a Blackboard? Like
so everything is there on the course webpage.
Okay.
Okay. So so whatever we covered in the last lecture is there on the course webpage, and there is a recording too, right?
Okay. Thank you.
So
I have a question as well. What did you say happens to if?
so if then is, in English, the implication is split into 2 parts, right? But it's just an implication, right? So we end up using 2 words when in logic we are just able to use 1 symbol right here. Okay, so if you will read this as if P and Q, then R.
Okay.
Okay.
Also, what is? Can you just explain? Well, P is proposition. What was Q and R? Sorry.
They are all propositions, right? Because they
Okay.
are all, simple statements that are either true or false.
Okay.
Right. So again, let's go back here as to what a proposition is. Right. Yeah, a proposition is a statement that's either true or false. Right. That's all. Let's see if I can. Okay, so so let's try more examples, right? So now in this exercise, we are, I'm already defining what the propositions are. So you get an A in the final exam is proposition P. You do every problem in the book, that's proposition Q, and you get an A in the course is proposition R, right? So now let's try to take each of these statements and turn them into formulas, right? So if you do every problem in the book, you will get an A in the final exam. Okay, again, final exam, not the course, right? So can someone tell me what is the formula that I should write down here?
Q implies R. It implies P.
Q implies P?
Mhm.
Okay, let's see. Q implies P. Does anybody think this is wrong? Okay, so if you do every problem in the book, so looking at the definition of Q, that matches that. And then, you will get an A in the final exam. So that is proposition P. And then we have a if then, so it must be an implication, okay? So let's take the second one, right? So you got an A in the course, but you did not do every problem in the book.
R and not Q.
Okay. Again, although I say, speak up. If you take turns, then it's a little bit more effective. I know it's a little hard because it's hard for me to see the whole class, so I cannot really, figure out who's speaking. So if you sort of, do this among yourself, and if different people take turns, then that makes that is much more helpful for the class, because it gives a sampling of where everybody is at, and that's really helpful for me. Okay, so so while saying all of this, I forgot what the answer was. Can somebody else tell the answer now, because the answer is already known? Yes? Okay, I'll wait.
R and not Q.
R and not Q, you said? Okay, so you got an A in the course, right? So that is R, but you did not do every problem in the book. So Q is to do every problem in the book. So if you did not do, then it is not Q, right? So, and but is, we use but in English, but from a logic perspective, it is the same thing as and, right? So you got an A in the course and you did not do every problem in the book. Okay, so okay, so in English, the word but is a conjunction, right? And is also a conjunction, and so it's not surprising that they mean the same thing in logic. So let's look at the last one. To get an A in the class, it's necessary to get an A in the final.
P implies R.
P implies R, you're saying?
Yeah.
Okay, what, anybody?
I think it's R implies P.
Okay, so let's write this down. Okay, So are there any other answers?
What about R does not imply P?
Okay,
Oh wait, never mind. I read that wrong.
okay, so let's,
Yeah, never mind.
I guess I can just do that. Okay, so what about,
What about not P implies not R?
okay, so I would think not P implies not R. No, no, no. Okay. Yeah, not P implies not R. So, so this basically says if you did not get an A in the final, then you won't get an A in the course, right? So in many ways, I would say that this is the closest to what is being said here, right? But you'll also see that R implies P is also capturing the statement, okay? And in fact, as we'll show later, this is a contrapositive of this implication, okay? A contrapositive is one where you negate the propositions on either end of the implication and you flip around the direction of implication, right? So we go from R to P, then we make it into not R and not P, and then you flip them around, okay? So first you may negate them and you flip them around, and you can see that you will end up with this. So both of these are correct, and this one is not correct because it doesn't say, the statement doesn't say that once you got a A in the final, you will definitely get an A in the course, right? Because P implies R says that if you get an A in the final, then you will get an A in the course, right? That's not what the statement says, okay? So again, sometimes, the statements are very easy to translate. Other times they do require just a little bit of thinking, okay? Any questions?
Oh, I was wondering what the 4 dots in front of the equal sign means.
I'm sorry?
I was wondering what the 4 dots in front of the equal sign means.
4 dots.
Like
oh, here.
P.
Here.
Yeah.
Yeah, I understand. Okay, 1 second. This. Yeah, this is, you can read it as R is defined to be, okay? Colon equals is, it's a way of defining things, right? I say R is defined to be, you get an A in the course. P is defined to be, you get an A in the final exam, okay? Okay, so one way we can understand formulas is by filling out truth tables, right? So basically, we consider every possible value for the propositions in the formula, and then write out what is the value of the formula itself, right? So in the case of P implies Q, we can fill in all possible values of P and Q. Right, so there are 4 possible combination of values P and Q can take. Okay, so now we can write out, okay, what is P implies Q. So if P is false, what is the value of P implies Q? So we are saying if P then Q should be true. That's what the implication means, right? So when P is false, well then, nothing is required of Q, right? So it doesn't matter what Q is, because the moment P is false, the statement holds vacuously, right? So if P is false, then a statement of the form if P then Q is going to hold vacuously, and therefore we are going to fill it out as true. So in the same reasoning applies here, because P is false, so the implication is going to be true. Then here is the interesting case, because P is true, but Q is false. So if you consider a statement if P then Q, now this part is true, but this part is false, okay? Which means that the whole implication is wrong, right? Because the statement says whenever P is true, Q should also be true. But then here is a case, we have an example where P is true, but Q is not true, okay? So therefore, this is a case where it is false. And similarly, true, we can do the same kind of reasoning and then say it is true, okay? So let's try to fill out something.
Can you explain again why if P is false and Q is true, then P implies Q?
Okay, so if you can either understand that from how you understand English, or if you don't, then you can take that as a definition of P implies Q. Okay, so you can either appeal to your intuition based on how you understand a statement of the form if P then Q, or you can say this truth table is the definition of P implies Q, right?
Okay.
So that's okay. So let's try to fill this other table here, which again we will. Right, so not P, we just have to negate. So this will be true, true, false, false. Now, if we do not P or Q, then not P, because it's true in both cases, this is going to be true. And then in this case, not P or Q. So not P is going to be false, and Q is also false, which means that not P or Q is going to be false. And here, not P is false, but Q is true. Therefore, not P or Q is going to be true. Okay, so that's how you can check the value of this formula, not P or Q. And one thing you will notice is that not P or Q has the same truth table as P implies Q. So we can say that P implies Q is equivalent to not P or Q. Okay, so many times if you find these two rows confusing, then if you think of P implies Q as not P or Q, then again that's another way to remove the confusion. Okay, so you can if you find it easier to think about implication in terms of as not P or Q, then by all means go ahead and do that. Okay, so that's that's perfectly reasonable. Okay, so now let's continue this line of investigation. So let's ask the question, does P imply Q imply not Q implies not P? Okay, so let me see whether I have. Okay, so one way to do this is, of course, we can fill out the truth table, right? So we can say P, Q, okay, and P implies Q, and okay. So let's try filling this the same way. False, true, right? So we can see when P and Q are false, then P implies Q, right? We already, we can fill this P implies Q column. So we can fill this column from the previous slide. So this is going to be 2, true, false, true. Okay. So now we are going to fill this one. Okay. And remember, once again, that we can think of this as not of Q or not of P, right? So we said A implies B is the same as not A or B. Okay, so we are applying this formula on this so that we have a second representation. And then we can cancel out these two negations, and then we have, right? So we have Q or not P. Okay, so instead of trying to fill out the value of this implication with nested negation, we will simply try to fill out this equivalent formula, which is looks a little bit easier to deal with, right? So Q or not P. Okay, so here for this case, P is false, therefore not P is going to be true. Okay, so therefore Q or not P is going to be true, right? Once again, Q or not P is true whenever P is false, right? Because whenever P is false, not P is going to become true, and that's going to make this whole formula to be true. So whenever P is false, we can quickly say that this formula is going to be true. Okay, so now let's look at P being true and Q being false. Now, since P is true, not P is going to be false. Okay, so this is false, so we can kind of ignore it. Now, Q in this case is also false, so this also becomes false. So we have false or false, which will become false, right? So similarly, we can look in this case, you'll see Q or not P, because Q is true. So this whole formula is going to be true. So this is going to be true. Okay. So what you see from the table is these two columns, P implies Q and not Q implies not P, right? They are identical, right? Which means that these two formulas must be logically equivalent, right? If the truth table for two formulas is identical, then that tells us that the two formulas are logically equivalent, which is the same as saying that if whenever one of the formulas is true, the other formula is true, and whenever one of them is false, the other is also false. Okay? So, and again, okay. So again, this is, we will talk about this again. So whenever you have an implication, P implies Q, right? It is true that not Q implies not P is also true. And we call this as the contrapositive, right? Contrapositive of P implies Q. So any questions so far?
How did you get not Q implies not P to be Q or not P?
Okay, so remember we said here, right? P implies Q is the same thing as not P or Q, right? So we actually, again, we had these two tables here, right?
Mm-hmm.
So one for P implies Q and one for not P or Q. We filled them out and we found that they are identical, right?
Mm-hmm.
Which means that the two formulas should be equivalent, right?
Yeah.
So therefore, and many times it's, people find it, less confusing to think in terms of not P or Q instead of P implies Q, okay? Because this notion that when P is false, P implies Q is true is something that that does not come naturally to everybody easily, right? After some time, of course, everybody is able to accept that, but initially it may not be that easy to understand. And so thinking of an implication in terms of a disjunction is easier, okay? So that's what we did. So we replaced this by not of this, the left-hand side is called the antecedent, and the right-hand side is called the consequent. Okay, so when the left-hand side, so we negate the left-hand side, so that becomes Q, and then we replace the implication by an R, okay, and then we leave the right-hand side as it is, right? So that's what we did. Okay, remember, to go from the implication to disjunction, we negate the left-hand side and then change the arrow to an implication, and then the right-hand side just remains as it is. Okay, so this is how, instead of trying to evaluate this, we evaluated that formula, which has fewer numbers of negation, and so it's kind of easier to evaluate. Any other questions? Okay, very good. Let's look at more examples. Does P implies Q, does it also mean not P implies not Q? Anybody wants to answer this question? Of course, we can prove, we can figure this out by filling out the truth table. But truth table, of course, takes a little bit of time. So I'm sure many of you know the answer to the question. So why don't you, one of you, tell me what the answer is and explain why that is.
Oh, can I answer?
Yeah, sure, please.
Okay. So since you said that since it's two negatives, then it reverses. So not P implies not Q actually represents Q implies P. And so P implies Q does not imply not P implies not Q, if that
Okay,
makes
so
sense.
that's what we just said about contrapositives, we can reapply, and then we can say that this is the same thing as saying Q implies P, right? So we know that P implies Q is not the same as Q implies P, right? So we know that these two are not equivalent. Okay, so so of course, again, we can use a truth table to show this, and in particular, and then you'll see the difference. Okay, but when possible, of course, we want to avoid filling out a truth table because the size of the truth table grows exponentially in the number of the propositions in the formula, right? So far we have been working with just 2 propositions, right? So with 2 propositions, there are only 2 to the power 2, 4 possible values, right? So because each proposition can be true or false. So if you have a proposition P, then that has 2 possible values. Proposition Q, that has 2 possible values. So the total number of possibilities is 2 times 2. But if you have an R and S and then T, then each of them adds a factor of 2. So if you have 5 propositions, so if you have a formula that's a bit complex and has 5 propositions, then you have 2 to the power 5 rows or 32 rows in the truth table. And you can imagine that that's going to take quite a while to fill out, right? So we are always, while there exists this, reliable method for checking equivalence or implication and so on, this reliable method can be very tedious. And so we try to avoid this tedious approach whenever we can. Okay, so now let's define some terminology. We have so far talked about propositions. We said contrapositive, and now we will we'll introduce 3 more terms: validity, satisfiability, and equivalence, right? So your formula is said to be valid if it is true for all possible values of the propositions in them, okay? So a very simple case is, P or not P, right? So you can see that P or not P is going to be true no matter what, right? Because if P is true, then this becomes true, therefore the whole disjunction becomes true. If P is false, then this becomes true, therefore the whole disjunction is going to become true. So no matter whether P is true or false, you have an example here that is, becomes true. And so this is called a validity, right? It's true no matter what the propositions are, okay? Now, satisfiability is a related notion. So we say that something is satisfiable if it is true for some values, right? So whereas we said for all values of the propositions, it should have the right, it should be true. Whereas what we are saying here is that there must exist some values for the propositions that make this whole thing true, right? So somebody is talking without being on mute. Okay, so most formulas are satisfiable, right? So for instance, you say P, right? Then P is satisfiable because, if you set P to be true, then for that setting, this formula becomes true, right? So, or we can say another example, P and Q, right? So if you set P and both of them to be true, then P and Q is true. So it's satisfiable, right? So if you take P and not P, right, then that is not satisfiable, right? Because if you make P to be true, then this will become false. So the whole thing will become false. If you make P to be false, then this will become false. And therefore, once again, the whole formula will become false. So this is not satisfiable. Okay. So just as P and Q and P are satisfiable, P implies Q is also satisfiable. Okay. So a lot of formulas are satisfiable, but there exist some that are not satisfiable. In particular, a negation of any validity is not satisfiable, right? Because a validity is always true, which means that its negation will always be false, right? And therefore, the negation of a validity is not satisfiable. Okay. Now, the notion of equivalence we have already talked about, so it's not anything new. So we are saying that the truth tables for phi and psi, right? Phi and psi, they match fully, right? On every row they match, therefore they are equivalent, right? Or in other words, for every possible value of the propositions contained in them, you know, they are either both true or both false. Okay, and we saw several examples in the previous slides. Any questions? Okay, let's continue here. So here is an example. So we take two formulas, not of P and Q, and then not P or not Q. And then we ask, okay, are they equivalent? Okay. And once again, we can fill out the truth table and we find that, you know, that they are equivalent. Okay. And in fact, this is the De Morgan's law for Boolean formulas, right? So most of you have probably heard of this law. If you don't remember it in the context of Boolean formulas, you probably remember it in the context of sets, right? So we have, you know, A union B complement equals A bar intersection B bar, right? So this is De Morgan law that most of you remember from your high school, right? So they are essentially saying the same thing. In fact, if you consider the universe to consist of just a single element, right? So there is, in this case, when we talk about a complement of a set, there is a universal set with respect to which that complement is being computed, right? So if you fix that universal set to consist of exactly one element, right, then your union operation on sets will be like a disjunction on the Boolean formula. So in fact, these two you know, operations on sets and operations on Boolean formulas are in fact very similar, which is why, you know, when we use this you know, this symbol with a curved bottom, right, we replace that in the case of Boolean with something that looks kind of similar, except that we make the bottom to be sharp. Okay, same way intersection and right, once again we are doing the same thing, right, because the two are actually very closely related. So let's try to you know, do some examples. So we defined, so the way to understand this is that you push the negation inside and then you flip the symbol. Okay, so if it was sharp side up, then you make sharp side down, right? Same way here, you again push the negation inside and then flip the symbol, right? So that's the, so De Morgan law works regardless of whether the internal inside symbol is a conjunction or a disjunction. Okay. So what is, let's try this. Can you lift your hand and let me see if I can figure out who has a hand lifted and ask one of you to answer the question. Okay, Dylan. Can you go ahead?
Yeah. So it's not P, or not Q, or not R.
Okay, so we can work it out by rewriting this, right? So we can say not P. Okay. Right, so we can rewrite this as not of P and okay. Right, and now we can apply De Morgan's laws. So we can say not P or not of Q and R, right? And now we push it further inside and then becomes not Q, right? So this one becomes that, right? So so we get this answer, right? So we can systematically apply it to derive it, but also we can remember that, you know, from this, we can say that, okay, no matter how many conjunctions or disjunctions are inside, you know, you can still push the negation to past them and flip them all, right? So we again flip, there are two conjunctions inside, we flip both of them and we push the negation to you know, inside of those conjunctions. Okay. So so how do we do this? Right. So now, Jenny.
Would it be not P or not Q implies not R?
Right. So the pushing inside is only for conjunction and disjunction, not for implication. Right. So we have to stop here and now figure out, you know, what is there some way to simplify it further, right? So one way to simplify it further is by doing what? How could we apply De Morgan's law further, because De Morgan's law doesn't go inside implications?
Could you maybe use the contrapositive?
That'll still be a implication, right?
Yeah.
I think.
Yeah, Andy? Andy, please, can you go ahead? Okay, so if you lift your hand and then, you know, I guess you probably have to, you know, unlift your hand or else it keeps showing up here. So Frederick, can you go ahead?
So earlier we learned that the logical expression not Q or R is equivalent to Q implies R, so we can replace that here.
Okay, so let's do that. So we will say this is not Q or R, right? And now we can apply De Morgan's law again. So we can say not P or, and then we'll just apply this, right? So push the not inside. So not will become, will cancel out. So this will become Q, right? And this R will become an and right? Okay, so so now, if we want to further simplify this, what can we do? We can use the same trick, right? So because this is of the form not P or something. So we can turn this into P implies Q and not R. Okay. So if anybody notices any mistake, let me know. But otherwise, let's. So by repeatedly applying these equivalences, we can arrive at what is called a normal form. Okay. So there are two kinds of normal forms. The first one we'll talk about is a disjunctive normal form, which means that at the outermost level, the operator is always a disjunction, right? So you have a formula of the form, right? So you have a formula okay, which is a disjunction of conjunctions. So each of the psi1, psi2 to psi n, they are all conjunctions, right? And what is a conjunction? Conjunction is, consists of either consists of a conjunction of propositions or their negations. So one thing you should see is that something like right? So this is not DNF, okay? Because for it to be a DNF, the all the disjunctions have to be at the highermost level, okay? So I'm sorry. Okay, so what I mean here is P and Q are R, right? So let me redo this, okay? So I will. Okay, so let's try here, right? So if you take an example of P and Q or Q and okay, so this will be your psi1, this will be your psi2, but psi2 does not satisfy this form, right? It does have a conjunction, but inside the conjunction should be just propositions. Whereas here inside a conjunction, there is a formula, right? With connectives and so on. So this is not DNF. So this has to be further simplified. And for that, we need to use the distributive property of conjunctions and disjunctions. So we have the property that P and Q are R equals P and Q are P and R, right? So this is called a distributive property, right? So if you apply the distributive property, then you can simplify this into P and Q are, then you apply the distributive property here. This becomes Q and P or Q and R. Okay, so now you have, you know, psi 1, psi 2, and psi 3, and all of them satisfy this definition, and so you have something in disjunctive normal form. So in general, by applying distributive and De Morgan's laws, you can reduce any Boolean formula to a disjunctive normal form. Okay.
Wait, sorry.
Yeah, go ahead.
I just want to clarify. So like when you negate the sign as well, right? So if it's like P or Q, like in parentheses, and you negate, it would be not P and not Q.
Okay, so let's. This is this what you're asking?
Yeah. So you always negate the sign as well, right?
Correct. De Morgan's law is you push the negation to each of the, you know, inside things, and then, you know, flip the symbol.
Thank you.
Wait, can you explain how you, a little bit more, how you went from, on this slide, hang on. Yeah, on the slide with the DNF, how you went from Q and P or R to that simplified form?
Okay, so we applied the distributive law to go from Q and P or R to Q and P or Q and R, right? So we just distribute, just like, think of it like, you know, 3 times 4 plus 5, right? We just say 3 times 4 plus 3 times 5, right? So that's a more familiar distributive law that we use every day, and it's the same law that's being applied here with just different operators. Does that make sense?
Okay, thank you.
Yeah. So again, you basically need to do these. You know, you need to be able to express implication in terms of and R. Then you can use the De Morgan laws and the distributive property, and with these 3 in hand, you can take any Boolean formula and reduce it to its disjunctive normal form. Okay. So just like disjunctive normal form, you can also reduce it to what is called a conjunctive normal form, which is very, very similar. The only difference is, you know, in the DNF, where you saw a conjunction, now you put a disjunction. And in the DNF, where you had a conjunction, you put a disjunction. So you just flip, right? So at the outermost level, there is going to be a bunch of conjunctions, and inside, okay, so, you know, that's wrong. You should say disjunction, and the example should be P1R, not P2. Okay, so conjunctive normal form is very simple. And then again, any proposition formula can be transformed into CNF in basically using the same tricks as the previous slide. Okay, so that brings us to a famous problem called the SAT problem, or satisfiability problem. So the SAT problem doesn't apply to arbitrary Boolean formulas, but it is applied to a formula in a conjunctive normal form. Okay, this is because a formula in disjunctive normal form, you know, its satisfiability is very easy to determine, because in a disjunction, all you need to do is to make one of the disjunctions to be true, right? So let's say this is the disjunction that you want to make true. Then you can make it true by setting P1 to be true, P2 to be false, and P3 to be true, right? So this conjunction can be trivially made true. And once this is true, anything that contains a conjunction, any disjunction that contains this conjunction is going to be true. So the satisfiability for problem on DNFs is trivial to solve. But in the case of conjunctive normal form, you have the requirement that you are whatever propositions you make true and whichever you make false, that should make each of psi1 through psi n to be true, okay? And that is what makes the problem difficult. And in fact, there is no known algorithm for doing satisfiability check on the CNFs in an efficient way. Okay, so the problem is what is called an NP complete problem. Okay, which means that we don't know of an efficient solution to the problem. An efficient solution is one that is that takes time, which is polynomial in the size of the input. Okay. In contrast, with respect to the SAT problem, the best solutions we know are exponential in the size of the input, right? So this is kind of intuitively, it's kind of makes sense, because if you have a formula with n propositions, then there are 2 to the power n possible truth assignments, right? We talked about these filling out a truth table. So if you fill out the truth table for this formula to see if there is any row that is true, right? So if you do that, if any row is true, then of course it's satisfiable. But that takes an exponential amount of time. Unfortunately, all the smart computer science researchers haven't come up with something that's significantly superior to that algorithm, right? So it is, of course, they know something better than filling out the truth table, but it's not something that's efficient enough to be very practical. And so the SAT problem has formed the basis of this whole theory of computational complexity, and it's called NP completeness. So it's something that you will come across in perhaps the CSE 350 course that you might take next year, or in the algorithm course that you will take in a couple of years from now. Okay, so let's stop here. If there are any questions, I'll take them. Otherwise, feel free to hang up, and I'll see you next week. And please watch out when if I may post some problem sets on Piazza at any time. Okay, but if I post it and if I want you to submit it, then of course you'll have enough time to do this. So I will give you at least a week to 10 days to finish your homework, but you should. But I may post it at any time, so that's something that you should keep an eye on. Any questions?
I have a question.
Yes.
Why is the conjunctive normal form made up of disjunctive propositions?
That's how conjunctive normal form is defined.
Okay. I just kind of like.
So so to get in order to turn everything into this form, either you should have, all the 3 operators should be there in the formula, and, or, and not, right? Mm-hmm. So you can't get rid of any of them. So if you choose to put all the ands at the outermost level, then the r's have to appear inside. If you choose to put all the r's at the outermost level, then the ands have to appear inside. Any more questions?
Where can we find this in the textbook?
So whatever we have covered, you will see textbook section something, right? So that's where I'm switching between sections.
Okay.
Yeah. But of course, what I'm teaching is not, exactly there in the textbook. But you will find that it is largely it's the same topic. So often you will find the examples are different, but the material is basically the same. Okay. And I can't promise I'll be able to do it all the time, but whenever I can, I will do that so that you have a second source of reference.
Excuse me?
Yeah.
I have a quick question about propositions.
Yeah.
So there's statements that are either true or false, but when you gave the example of things that aren't propositions, you said something like tomorrow will be sunny. Isn't that true or false? Or am I missing something?
Yeah, it can't be true or false because you don't know whether it is true or false, right? You can't say right now whether it's true or false.
So you can't say that like predictions about the future are propositions?
Right, because you don't know whether they are true at this point.
Okay, so you have to know it at the moment for it to be a proposition?
Yeah, there is no notion of time in,
Okay, thank you.
in here, right? Our opinions or, many other things. It's just simple, it's true or false. Anything else? Okay, then I'll hang up and see you again on Tuesday.